Welcome to Module 17 of Database Management Systems course in IIT Madras online B.Sc program. From the last module, we have started a little formal discussion about the foundational mathematics of relational database. We have discussed about relational algebra and its operation in some depth. We will continue on that stream, but just take a quick look into the calculus based query languages through the equivalence with relational algebra. We do not intend to really go deep on the calculus because first of all, for two reasons. One is the calculus needs more in-depth foundation on the results of predicate calculus, because they are based on predicate calculus, and the other is they are all equivalent to relational algebra. So, just following one model on which particularly SQL is based would be quite okay for our future discussions, but it will be good for you all to know that these kind of models exist and what is their interrelationships with between themselves. Right? So, the first one in the formal relational query language we have already done. The second is what here, second and just glimpse of the third we will take. Now, before I get into tuple relational calculus, the first language or the first model, let me just take a quick look at predicate logic, because I am not sure how much of predicate logic you are familiar with, but a few basic definitions are required for the entire of this calculus. So, predicate logic or predicate calculus, these are two names interchangeably used. So, in some places it is called logic, some places it is called calculus. It is an extension of propositional logic or propositional calculus, or what more simply is called Boolean algebra. So, what do we have in Boolean algebra? In Boolean algebra, we have say variables, Boolean variables or propositions, which can be either true or false, right? Either true or false. And we have a few operators, three operators, right? Say something like this, and or not, and we using them we can write any number of formula, and once the truth value is assigned to these Boolean variables, we evaluate them to get a final truth result. Right? So, that is the basic formulation of Boolean algebra or propositional logic. So, you have propositions or variables which take true or false value, and based on that you have a result. When it comes to predicate calculus, you add a concept, you still have propositions, but you add the concept of predicate and quantifiers to better capture the meaning of the statements, which cannot be captured adequately, appropriately, precisely in terms of the propositional logic. Right? So, that is the extension. So, that is, these are the key things to note: predicate and quantifier, plus the propositions A, B, C, D, all variables which could be true or false. Now, tuple relational calculus and the domain relational calculus are completely based on predicate calculus. They are basically certain forms of predicate calculus. Right? Let us take a quick look at what these predicates and quantifiers are. You may know, but it is always good to discuss for completeness. So, suppose I make a statement that x is greater than 3. Right. If you look into this statement, there are two things in this. One is the variable x. I do not know what its value is, but it is a variable, right? Normal variable which can take some number 17, 23, 112 and so on. And the second part is a property. Second part is actually a property, right? So, it says that is greater than 3. So, I have a variable and I have a property. Now, this part, the property, is called the predicate. It refers to the property that the subject of the statement x can have, may have or may not have. So, what we do is we denote this typically in this kind of a notation, where P is the predicate such that, and x is the subject of that predicate, x is a variable, so that this predicate, once I put a value to x, this predicate is evaluated and becomes a proposition. So, Px is a predicate, but P5 is a proposition which has a value true or false. P2 is a proposition which has a value true or false. Naturally, if my predicate Px is x greater than 3, then P5, the proposition P5 is true, the proposition P2 is false. Alternatively, you can think about a predicate as a function, because it tells you the truth value of Px at the assumed value of x. Right? So, you have predicates, you can again write conjunction, disjunction, negation with these predicates. You have a predicate calculus expression. Once you put values, truth value, once you put the different variable values x, y, z, whatever, they become propositions. So, it becomes now from a predicate calculus formula, it becomes a propositional calculus formula, a Boolean expression which you evaluate by the rules of Boolean expression, and you finally have a truth value. The difference being that now you are associating properties with variables which are not necessarily Boolean, which are not necessarily binary, which can come from any domain and can have any property, and a combination of those gives you to capture the truth value. So, this obviously subsumes the entire of the propositional calculus, but has a lot more. Now, certainly it is not limited to one variable. So, I can have any number of n number of variables for a predicate, and I can denote them. If a predicate does not have a variable, it is a proposition. Right? The predicate logic also has, alongside the predicates, they have quantifiers. Quantifiers are used to talk about properties that hold over the entire domain of discourse in a certain way. Right. Now, I said x is greater than 3. So, what is the domain of discourse for x? I can say it is a natural number. It is a natural number. So, if I say it is a natural number, then it is the whole of the natural numbers. Now, there are certain properties which I want to know whether it holds, how it holds over the entire domain of discourse. So, the first quantifier is known as universal quantifier, where it has a property which has to hold over the, why is it universal? Because it talks about a property that has to universally hold true over the whole universe, which means it must be true for all elements in the domain. Only then that quantification is true. So, the way I say, so it is written in terms of this notation for all. So, I say this is a quantified formula for all x px. Now, px, depending on the value of x, px may be true or may be false individually. So, what is for all x px? It means if I take any value in the domain of discourse, I can specify that domain or it can be implicitly known. If I specify any value in that domain and for that if px is true, then this entire statement is true. This becomes a new predicate. So, I say that, well, I am looking at a statement x plus 2 is greater than x. If that is my px, does this hold? Obviously, no matter what you take the value of x as, any real number, natural number, x plus 2 will be always greater than x. So, I say that for all x, px. I say my predicate mx is x is mortal, where the domain of discourse is the population of the world, human population of the world. What is for all x mx? It is true, which in proverbial terms we say men are mortal, means human beings are mortal. So, that is a universal quantifier. Let us say that we were saying that earlier we saw that px is x greater than 3. Now, what is for all x px? Over the domain of discourse, natural numbers. This quantified formula is not true. It is true for 4, true for 5, true for 1000, but it is not true for 3, true for 2, true for 1 and so on. So, for all x, px, x is greater than 3 is not true. Right. But if I say my domain of discourse is all positive numbers having 2 or more digits, let us say my domain of discourse is all positive numbers having 2 or more digits, then px x greater than 3, for all x px is true. So, you can see that the truth is always with respect to certain domains, and with respect to that we are saying that if it holds universally, then it is a universally true, otherwise it is false. Right. So, let us move on. The other is existential quantifier, which is on very similar lines, where it says that does there exist at least one value in the domain of discourse where Px is true, it is written in this way: there exists x Px. So, if we go back to Px being x greater than 3, then for all x Px, assuming the domain of discourse is natural numbers, for all x Px was false, but there exists x Px is true because it is true for 4, true for 5. So, at least one. So, these are the two kinds of quantifications which we often need to model. There are other kinds of quantifications also, but not so popular, or rather, to put it in different terms, they are expressible in terms of these quantification and the predicate. So, we move from propositional calculus to defining predicate and quantification, and that model is what is the model for is what the tuple relational calculus is. So, in tuple relational calculus, all that we do is very simple. We say that the formula or the relation is basically a set of tuples T where Pt holds good, that this predicate holds good. And predicate may have various conditions, combinations of and or not, it could have quantifiers and so on and so forth. Right? So that is the basic idea. So, these are the different component of the predicate calculus formula. Attributes would be there, constants would be there, comparison operators, connectives, and or not, implication, x implies y, which actually means not x or y, and quantification. So, these are the possible formula for the tuple relational calculus. Couple of quick examples, say we are talking about obtain, this is a student's database here, obtain the first name of the students whose age is greater than 21. So, what we are looking for is say if T is the relation, then we are looking for the first name. It is T dot first name. What will have to happen? What is the domain of discourse? The truth depends on that. The domain of discourse is a relation student. So, student T. Student T is a predicate such that if T is a tuple of the student relation, then student T is true, otherwise it is false. Right? So, this will make sure that this is equivalent to saying in different terms, okay, this is already written here, that T is an element of student, you could be writing it this way. And age is greater than, so T dot age is greater than 21. So, that defines this answer to this query. You could write it as a set member. You could also write it like this, that it is a set of tuples T, set of names T such that your there exists a tuple S with age greater than 21 and T name equal to S name in student. Just different ways of writing the formula, means practically the same thing. So, everything that we want to query on can be in this way written in multiple predicate calculus formula. Find the names of all students who have taken the course named DBMS. Right. So, what is that we want? That for every student, there is a course taken by the student called DBMS. Right? So, let us look at the second one, say S dot name, you want the names, domain of discourse has to be a student. Then we say that there exists a course C having the same ID as what the student has taken. The domain is getting refined, courses that the student has taken is S dot course ID. So, there exists a course C having the same ID and that course has the name DBMS. And when you evaluate this C, you do it in course table. Answers that. You can look at it differently. S is a student, C is a course. So, that course ID is same and the name is DBMS and the student's name matches. That is the result. So, that is basically the way to express in terms of predicate calculus, or in this case the tuple relational calculus. There are other queries. Let us look at this one. So, there are flights, flight number, starting point, ending point, distance, departure time, arrival time. There is a aircraft with ID, aircraft name, cruising range, how far it can go. This certified, so there are employees which are certified on aircrafts and the employee details. These are the 4 tables. So, the query is find the EIDs, employee ID of pilots certified for Boeing aircraft. Find the employee ID of pilot. This is your final result. Right. Certified for Boeing aircraft. Right. So, you need the employee ID, certified. So, you need the certified. You need the Boeing. So, all these will be involved. Right. Now, the first thing you need is, how do you find what are the employee IDs that are available for the Boeing aircraft, that are certified for the Boeing aircraft? Naturally, these two will have to come together, right? And what works for that? If you just think the relational algebra way, the natural join between aircraft and certified. This will give you a relationship between employee ID and aircraft name, which could have Boeing. So, now you filter this for Boeing, you are just interested in the Boeing part of it, nothing else, no other aircrafts. So, you filter, so you select on Boeing. So, whatever will remain are the employee ID of those who are certified to fly EID. Here you have been asked to find the employee ID. If you are asked to find the name, then what you will have to do? You will have to again, because the name is available in the employees. You will get the names. So, that is if you look at it in the relational way. Let us look at it in the calculus. It is very simple. In calculus, actually it is easier, because what you are looking for are the certified employee IDs, C.EID. C has to be certified, it has to come from there. A has to be an aircraft which has a name Boeing, and the certification of the aircraft ID available in the aircraft table and the aircraft ID available in the certification table has to match. That gives you the entire query. Right. So, this is how, I mean, you need to practice a lot to be able to write this. There are a couple of examples given around here. We can take them up in tutorials also. Now, So that's tuple relational calculus. It's just logical thinking, nothing other than that. One point I would like to mention is before I close is that you have to make sure that expressions are safe. What does it mean if expression is safe? It means that the result of your expression cannot be infinite. Right? It has to be finite. But so you would say, how can that happen? How I'm working with finite sets. How can it suddenly become infinite? It can, because for example, I say that this is my predicate set of tuples T such that T does not belong to relation R. Now that anything in the world can not belong to relation R, right? So you have to be careful about that. At least if you have any attribute in the relation which has an infinite domain, then you must be careful to avoid that. Normally, it will not happen when you are working within a SQL kind of situation, because it is well taken care of within the SQL itself. The domain relational calculus, I will not go in details. There is practically no difference between the tuple relational calculus and domain relational calculus except the notation. In the tuple relational calculus, you have variable for the entire tuple clubbed together. In domain relational calculus, every attribute is a different variable. So, you have a Cartesian product of that, which is the. So, if I have NRE tuple, then in domain relational, in tuple relational calculus, I will call it T. In domain relational calculus, I will call it the attributes x1, x2, xn. So, what becomes NRE, you use. So, it is just a different way of syntactically writing things, which makes it different. Conceptually, there is absolutely no difference between the two of them. Now, finally, the question is, the three models are the same. Now, in some cases, we have worked out, there is a formal proof for everything. What the way you go is basically for every relational algebra operator, if you can show how do you write the tuple calculus expression, then you will know that that is equivalent, right? That is it is. Similarly, for every tuple calculus predicate, that is conjunction, disjunction, negation, quantification, if you can show what is the equivalent in the relational algebra, then you will know that both of them are equivalent. So, just showing you an example here, that this is a selection operator, B is equal to 17 on R. So, we know that in tuple calculus it can be written like this, and if the relation has two attributes in domain calculus, it can be written like this. Now, this is by example. You can try to prove it in general. I am not going into those because we want to keep closer to practice. These are things that people have worked on and have proven long ago, and you can take that fact. So, all that I have done is, for every operation I have just given one example to elucidate that what is the kind of structure that it equivalently takes. So, this is a projection. So, when you take a projection, how you can write it in terms of tuple calculus and so on. But we would not go into the detailed mathematical proof of this. The proof is given in the book. If you want, you can read it up. But just go with the fact that there is equivalence for each and every operation and their combination between relational algebra and the predicates in the calculus. So, this is for union, set difference. You can just see through that when you are reading through these slides, the Cartesian product, everything natural join. So, it looks little cumbersome when you write down natural join, but you can always, it is always possible to write down a natural join in tuple calculus, because it is possible to write Cartesian product and the rest of it is just selection under different conditions. Division too, though division is not a fundamental operator, so this is not necessary for the equivalence proof. Okay, so With this, we have discussed the tuple relational and domain relational calculus, the basic framework of that. I said that I'll be at the overview level, and primarily we'll continue to use the relational algebra, and we just mentioned an outline of how you can probably go around looking at the equivalence of them. So, we'll close the module here now. Thank you very much for your attention, and see you in the next module.